Welcome everyone to today's webinar, Introduction to Water Quality. I am Mackenzie Bean, Managing Editor with Becker's Hospital Review. We will begin today's webinar with a presentation and we'll have time at the end of the hour for a question and answer session. You can submit any questions you have throughout the webinar by typing them into the Q&A box you see on your screen. We look forward to hearing your questions. This session is being recorded and will be available after the event. You can use the same link you used to log into today's webinar to access the recording. Today you'll be hearing from Seth Sandy, who is the Clinical Educator Coordinator at Healthmark Industries. Seth provides clinical expertise on medical device reprocessing, SPD education, and standards. Prior to joining Healthmark, Seth spent 20 years as a central services professional, primarily focusing on education for the last 8 years. He was responsible for providing continuing education to ensure the SPD staff remained certified and were conversant about the latest trends and requirements of a sterile processing area. He also had responsibility for competence verification and documentation activities within the department. So Seth, thank you for being here today, and with that, I'll hand things over to you.
Thank you very much. Hi, my name is Seth Sandy. I have a quick little disclosure here. I am an employee of Healthmark Industries. I am involved in the manufacture and distribution of medical products. The opinions expressed today, while are scientifically based and things like that, are opinions of the presenter. And this is to reflect techniques and approaches and opinions of the individual presenter. Healthmark, this is just our policy and philosophy statement that we do before every presentation, because we really do believe in education and that an educated customer is a great customer. So we do our best to get out and make sure everybody has the most up-to-date and current knowledge. I just have a couple of things before the objectives to really talk about how important water is. And this is just a quick little thought to keep in your mind as we talk about water, the way that we use it, that water is a huge issue around the world, and not even third world countries. You know, if you're Flint, Michigan, things like that, you know that water quality can impact anyone, anywhere they live. We're going to get kind of specific with how water affects us in the medical industry right now. And so my last little thing before the objectives is an article from January 2018 where water quality impacted surgery at a VA, and they had to reschedule surgeries because they were seeing issues that were caused with water quality. So it can happen all over, and it does affect many things. So our objectives today, we're going to define and understand the role that water plays in the medical facility with an emphasis on device reprocessing. We're going to review the 3 major factors that impact water quality, which is hardness, temperature, and pH. We're going to review the standards, guidelines, and instructions for use that prescribe the quality of water that we must use. And there are several places we're going to get that information from: AAMI, AST, AORN, and of course, device manufacturers have something to say about water quality as well. Understand how poor water quality can contribute to poor outcomes in patient care. So right to objective number 1, we're going to define and understand the role that water plays. So one of the issues facing medical device reprocessing professionals is ensuring that they have the quality of water specified in IFUs, and especially if you're doing flexible scopes, and we're going to talk about this a little more later on. There's several levels of water, and you may need to have more than one, and most likely would need to have more than one to process certain devices. But it's used in many processes throughout the reprocessing area. We think of it for cleaning, of course, and tap and potable water is used for most steps in cleaning, but a lot of final rinses now are looking for treated or critical water. But we do see it used in the assembly process. There are many departments that flush lumens. You have to be very careful when you're doing that on the clean side, because if something is dirty, you have to watch out for that. But that is something that you see. And then, of course, it affects the sterilization process in the form of steam. So each of these pieces of equipment is directly affected by your water. Your sinks, you know, that's your investment in your equipment in decontam, stainless steel sinks and things like that can be dramatically affected and the life shortened by poor water quality. So sinks, sonics, AERs especially, washer disinfectors, cart washers, and sterilizers are all pieces of equipment we have in departments, and they are directly affected by water quality. The quality of water used by sterile processing for device processing has considerable influence on that biggest investment, and that is instrumentation. All types of instruments, from your stainless steel instruments all the way up to probably one of the most expensive pieces of instrumentation to buy now, which are flexible scopes. And poor water quality is going to equal poor outcomes. You're going to have to re-clean or do any number of things to try to combat having poor water quality. So what type of water should we be using in our department? Well, at its base, tap water is usually potable. That's being called utility water. Now a lot as we get into definitions for things, water gets softened a lot too, and that's where the water hardness is going to come in, and we're going to talk about that shortly. And then you have DI and RO, so your deionized and your reverse osmosis water are usually the four that you see most commonly in most facilities today. So let's break them down a little bit. Let's define those. Potable water, water that has been treated and delivered in a manner so that it meets EPA guidelines as suitable for drinking. That sounds pretty good unless you watch TV and have seen the commercials for water filtration systems where it says this water has an acceptable amount of lead. You know, so when we start to think about potable water, it can still be on a level that maybe an instrument manufacturer would not recommend, especially for a final rinse. Softened water has had a technique that removes ions that cause water to be hard, usually calcium and magnesium, but iron ions may also be removed by softening. And now we're into actually critical water. Our DI and RO water is considered critical water. Water treated processes that use specifically manufactured ion exchange resin to remove ionized salts from the water. And our reverse osmosis is membrane separation process for purifying water that is based on a molecular sieving and ionic rejection that is effective in removing ions as well as dissolved organic contaminants with a molecular weight above 100 parts per million. So now we're going to start to talk about those things that affect water, especially pH, hardness, and temperature. In this little picture here, I hope that the back of your washers do not look like that. This is a place that obviously has hard water issues. That's a lot of scale and stuff going on. And that's, if you start to see those things, it is an indicator that your water may not be where you want it to be. So we'll start with hardness. That's one that people are accustomed to the most. Water hardness is defined as the concentration of calcium and magnesium, as I said before, expressed in calcium carbonate. So these and other minerals bind with cleaning agents in detergents and prevent them from reacting with soils on instruments. So we want those cleaning agents, we want those enzymes and things to work for us. They're supposed to help us. And if things in our water are binding them up and using them up, then we're not getting the effect that we want and the help that we expect to get from our detergents. The amount of these minerals and other dissolved solids in water present obstacles to good cleaning. They absolutely do. Hardness minerals can cause spotting and filming on instruments. They must be effectively tied up or sequestered if the cleaning results are going to be satisfactory. And that is what the inside of a pipe can look like if you're having water problems. And that kind of stuff doesn't stay deposited. And the deposits themselves are coming from what is in the liquid water anyway. So it keeps moving through the system, and it's going to end up in places that you don't want. It doesn't just stay in the pipes. The mineral salts react with soap to form an insoluble precipitate known as soap film or soap scum, right? That actually is a little bit of a biofilm, and that is really how it starts to affect cleaning. When soap film does not rinse away easily, it tends to remain behind and produce visible spots, and that's where someone says, "Oh, I have water spots. I have hard water stains." That's really what they are. Some of the soap is used up by reacting with hard water minerals to form this film. So it is really reducing the amount of soap available for cleaning. This may actually cause you to use more soap. So you have to start to think about it that way, that my water quality might actually be causing me to use more detergent than I would if I had better water quality coming to my department. Most detergents we use are low foaming. Thus, if you see a lot of foam, it could be a warning sign, right? We want them to be low foaming, but if they're reacting with hardness minerals, you may actually see more foam, and that could be just a visual indicator that you're having water problems. So here's just a little guide. So a way to think about water. We have charts for a lot of things. I'll show one about pH coming up. And so measured in parts per million, 0 to 60 is soft water, right? And would not need much softening, if any at all. And once we start to get once we start to get higher in the parts per million, then we need to start taking some action. You can also have that in grains per million. That's a way that it's measured too, but most of us are familiar with parts per million. And if you're at that very hard stage, more than 181 parts per million, you absolutely should be softening your water to use at any point in the cleaning process. So now let's talk about pH. So the pH scale is measuring the acidity or alkalinity of a liquid. The pH scale ranges from 1, which is very acidic, to 14, which is very alkaline. The midpoint between them would be 7. And so, pure water, that's a term people kind of use now, would be around a 7. Milk would be very close. If you've ever wondered why having a glass of milk after having your hot chicken wings or things like that works, well, that's a neutralizer. You're coming back to that middle ground of a 7 with something like that. So here's the scale that I mentioned, just a simple scale. I think everyone's pretty much familiar with that. And if you're reading any of your instructions for use for your detergents and things like that, most of them are looking for neutral pH, right? That's a pretty ubiquitous term that we see throughout standards and things like that. So the pH scale is logarithmic, which means that the steps in between the numbers increase by 10 times. Therefore, as the scale moves from 7, each step is 10 times more alkaline than the last, and conversely, it's 10 times more acidic as you go down the scale. So what is alkalinity? That's just I'd thrown this one in here, and temp will come next, because alkalinity is a thing that we hear, and sometimes it's not well defined. Alkalinity is a measure of the buffering capability of water to resist a change in pH. So no matter exactly where in the pH level you are, you're looking for a decent amount of alkalinity to hold that, right? So it's desirable at every given level of pH to have a higher alkalinity, because then it will hold where you want your water to be without letting it move up and down the pH scale easily. So now here's our other, I call it the fourth factor now because I threw alkalinity in there, but the other factor that we're talking about is temperature, which absolutely affects and has a huge effect on water. So when it comes to cleaning, hotter is better, right? We think about that really in the wrong way. It starts with doing dishes at home when you're younger. It seems to get things off when you are dealing with something, like your dishes at home. But when you start to deal with things like blood and other things that we deal with in the medical industry, it's not the same. It does need to be at the right temperature eventually, and at higher temperatures eventually, and we'll define some of those as we go along. But hotter is just not always better. It can't be thought of that way. So proper temp absolutely varies from stage to stage. The proper temperature also varies on your cleaning agent, because at the wrong temperature, those enzymes, again, the things in the cleaning agents and the detergents that we want to help us, we can actually harm those enzymes with the incorrect temperature of our water. And Amy ST79 recommends monitoring your water temperature for those exact reasons. And why is it so important, really? The denaturing action of heat on blood makes it insoluble, and it interferes with cleaning. So really, especially with blood, if it is too hot at the beginning, then we can cook blood on. We can denature it and actually make it much harder to dissolve and wash away, and make it much more adherent to the surface of the instrument that we're trying to take it off from to begin with. So low temperature to start to prevent that denaturing, and then your higher temperature later to maximize your detergent cleaning efficiency is really how the best way for your water temperature to go throughout your cleaning process. The use of recommended temperature for all cleaning agents. That is something that will be stated on all of your cleaning agents. And if you're not actually looking to make sure that you're staying within that range, then you may be sort of hamstringing your detergents. They're not going to work as well if you're not using them at the range the manufacturer says. So here's just a little breakdown by part of the cycle. Oh, it's missing. That should say 90. Okay. So at pre-cleaning, cold utility water, the temp should not exceed 90. Because again, at about 104, we start denaturing. So we want that to be cool. I'm not sure why that number disappeared there, but that's what that would be. Once we hit our enzyme wash, oh, I'm sorry, there's a little piece in here, each one of these defining the kind of water as well. So that's cold utility water, and blood can be washed away with cold water. We don't need a ton of chemical action just yet at that part of cleaning. Then we move to enzymatic wash. That is utility water again, and that water should meet the enzyme detergent manufacturer's criteria. Typically, you see it about 110 to 130, depending on the manufacturer. Then we get into our main detergent wash. This is again with utility water. The detergent selected should be compatible with tap water in your region. So again, you know, if you happen to know that you have specific water because of where you live, seeking out the right detergent and the one that's formulated to work best with your water is going to give you the best results. The wash temp range there has gone up just a little bit again, right? About 120 to 160 there. Now we're in the rinse phase. That is warm or hot, again, utility water, although critical water, so that treated water, DI or RO, could be called for depending on the instrument or device that you're processing. And then our final rinse and thermal disinfection really should be with critical water. And that should be considered based upon the category of device that you're using. Some manufacturers recommend the use of critical water for the final rinse for all categories of instruments. So they don't say, well, because it's a this or because it's a that, and list them out. They just say, hey, critical water is best as a final rinse no matter what. And then, of course, to get thermal disinfection, we really finally do want our water to be hot. We need that at least 180 for a minute, usually 180 to 194, and that's where we're actually getting the thermal disinfection that we want out of the last part of our washer cycle. Maximum temperature of the water should be compatible with the items being processed, so please don't melt anything. That is why That is why your washer is going to have different cycles, like the plastic cycle and things like that, because the device has to be considered for sure. So at the correct stage, as I said, we do want our water to be hot. And that's because water has a high thermal conductivity, so 20 times greater than air. It is actually able to move temperature, bring it in and pass it off or release it to the next thing, which is what we want, right? We want it to contact instruments. When it's rinsing and it's giving that thermal disinfection, we want it to contact instruments and raise their temperature up for that thermal disinfection to happen. Thus, it is an excellent medium for transferring heat required to destroy those microorganisms. So when you maximize the direct water contact with the surface of a medical device, that's what you're getting. That's what you want. Medical automated washers offer low to intermediate thermal disinfection. So we say thermal disinfection, but we're not saying high level. That's just a qualification there. Thermal disinfection isn't high level disinfection. It's low. It's considered low to intermediate. And just as a side note, your dry temperature, which can get over 200 degrees, and so that gets brought up occasionally. Well, you know, my dry cycle, when it finally kicks in, is about 215. That doesn't work. We just discussed how inefficient air is compared to water for transferring. So that's why the thermal disinfection happens in the rinse, and it can't be counted on in the dry cycle. There are some really easy ways to monitor water temp. ST79 says we should, so how can we? You can go with something digital, happens to be a little dosing system there, but that dosing system also has a digital thermometer that reads the temp for you. It can be as simple as just sticking a sticker into your sink that changes through contact, and that's the top right picture. And then, of course, when you're talking about running something through the washer, we do have the power now. We do have the technology to be able to go in and run something through an entire cycle and plot it out. And that's really what a data logger is, and that's what the bottom right-hand corner picture was. This is what that looks like. So there's actually more to the cycle than this. This is what about half of a washer cycle looks like when you put a data logger in there that's holding on to time and temp as it goes through. So you can see pre-rinse and enzyme are blended, and there isn't enough time. That typically needs to be around 3 to 5 minutes, and it doesn't quite have that amount of time. It's a little bit short. Then you see our next kind of issue is that it's too high in the enzyme cycle. It's 140 Fahrenheit it hit, and most enzymes die at and above that temperature. Usually enzymes are around 120, and that's where that was one of the things that I had said before. So think about that. There are enzymes in your detergent. We want them to help us, but enzymes can be killed just like anything else. It's actually a little organism, and so we can come along and lessen the effectiveness by killing those with too high a temperature. And then our detergent cycle was a little bit too low. That should be around 150, and that dropped down below that 140 range. And so, as I say, this is about plotting half a cycle here, but it's a great way to do it. There are ways to go beyond. I will say, also in some of those recommendations, the easiest thing to do is to check your tape. So that you will actually find that in recommendations that say before a washer is unloaded, the verification of the cycle can be done by viewing the tapes, and that's why we keep those. If you've ever sort of wondered why do I have to keep so many of these documents and so many of these things, it's so that we can verify those kind of things. So there are very high-tech ways, there are very simple ways to do it as well. So poor water quality isn't just a cleaning issue. Impurities can build up from poor water, and steam quality affects the sterilization process, causing deposits on your instruments. So some stains appear after the sterilization process, and I'm going to show a couple of pictures of some things that do not look so great because of what's coming out of the steam. Inner walls of your sterilizers can not look so great as well. If you're having water issues and you don't have them cleaned regularly, you can have some pretty ugly looking internal walls of your sterilizers. And then it can leave residues on tray liners as well if that's something that you use. It may also cause wet packs, right? We want good dry steam. I've always thought that was an interesting term, but it's true. At the right pressure and temperature, steam is dry, and it dries easier. And so if you're having water quality issues, that can totally affect that. It can affect inside the tray or package. It can affect outside the tray or package. And sometimes you might see an outline of a tray on the liner. That really meant that it was wet, and that was kind of dripping down, and the liners just picked up the outline of it. So some causes for those, steam filters. There's a few steam filters throughout your steam lines, and that's totally could be an issue. The cleaning of your steam traps absolutely can affect it. Your steam or water quality coming into your boiler and then out of, because those have to be treated as well, can be a problem. And then poor rinsing from the cleaning process. And then there can be other factors that are, that affect it as well. So sources of steam stains. Here's just a little poll from one of our standards organizations. Facilities should not use boiler additives and feeder water conditions on a batch basis. So now we're talking about, as I said, there's boiler additives. There's things that have to be done to boilers to keep them and to keep the steam in the right balances and things like that. And so you have to be careful and do that in the right way. Adding boiler additives or feed water conditioners to the steam in the steam distribution system, or use animus for conditioned steam lines. So those are things that you have to be careful when you're doing, and then you're monitoring the steam system as well. Healthcare facilities should provide for the preventative maintenance, repair, and monitoring of boiler and distribution lines that provide steam for sterile processing and document corrective actions. So they're saying you need to be watching it, and not only when you're watching it, are you recording what you did when you found something out of whack? And those are things that someone can come in and say, hey, I'd like to see the records for your boiler maintenance, and I'd like to see any corrective action documents. When you notice that it was not in spec or not the way that it should be, what did you do about that? And you should be able to produce those. So like I said, I was going to show some examples of what that looks like. So there's little, steam traps, U-bends, anything like that. Elbows is a place where things start to sort of accumulate, and poor steam quality causes these deposits, and they don't just stay in the pipes. It would be one thing if you were just looking at that pipe saying, well, I can't really see that. Well, they don't stay there. They come through those pipes. They come into the sterilizer, and the little picture in the bottom right corner doesn't look a whole lot better, the inside of the sterilizer, as opposed to the pipes on the left-hand side. So do you have deposits on your peel packs? That's, the paper there that's where the steam comes through. And so when you start to have there are telltale things you can start to look for, and that should make you say, well, maybe I should look at my water quality. So if they have copper piping delivering the steam, then that could be a possible source, is corrosion, and it can occur and then redeposit onto the pouch as it comes through the line. So some medical grade paper are more absorbent than others. And so, you know, you can have some of them hang on to it just more than others do, if that's not the greatest quality. And then poor rinsing of instruments. So not so much blood, but we're talking about residual detergents, right? So if they're left on instruments, the steam comes in, they become wet again, and then they can deposit back onto the back of your peel pouch. And then, of course, wet steam. You know, you would actually see that as well, as was really a wet pack or on its way to being a wet pack, and it just dried out just enough, but you can tell that it was very, very wet at some point, and that's not good. That's not what you want. So now we're up to objective number 3, where we're going to review the relevant standards and guidelines that prescribe the quality of water you must use in a medical device reprocessing department. And as you can see, there are several. We get them, and we really take it from any input that either has scientific-based recommendations, and those are AMI, AORN, so those are our sort of best practice organizations where people get together and we have consensus. But then we also take them from, of course, device manufacturers and detergent manufacturers, because they had to prove that cleaning worked and was facilitated well to the FDA before they could market. So taking their recommendations and staying within their guidelines for temperature and water quality mean a lot to making their product work well. So who is telling us what type of water to use? Well, absolutely instrument manufacturers, especially in that all-important final rinse. Detergent manufacturers, for sure. They know how their things work. Cleaning equipment manufacturers. So now we've got really all three of those things are sort of what work together, right? We've got our instruments, which are being exposed to detergent many times in our cleaning equipment, and those three right there should harmonize. We would like them to, and sometimes it's very difficult to make that happen, but that's something that you really need to be trying for. Professional groups like AMI, AORN, and APIC, of course, and then you have governmental groups, the EPA, the FDA, and the CDC have statements and I don't want to call them opinions. They have things that they support for water quality at certain stages, and all of those should be considered. So what are they based on? Well, a lot of them are clinically relevant and evidence-based practices. It comes from peer-reviewed literature. There's plenty of articles out there about water quality, and I suggest that you pick one up and give it a read, because you will probably learn something about water just by kind of going through that. Manufacturers' research and guidance, research and science. Unfortunately, some practices do not have the evidence to support that. So this shouldn't be hearsay. It shouldn't be like that. There are ways to look it up. There's information out there, and we should try to be using that to get our best results. So all major groups support water quality in principle, right? It's a quality improvement process. It's a quality assurance process, and monitoring the water is important. And then, so other major documents, the EPA, IFU, AMI, and there are others that put out things about it. We're going to talk about TIR 34 in a second. That's AMI's document about water quality. So the info is out there, and we should just be looking. So, as we previously discussed, poor water quality affects water's ability to work with detergents and remove soils, really affecting its fluidics. Why does that matter? Well, the CDC puts out a statement, a simple but sort of profound statement, if you think about it, for cleaning. Cleaning is done manually in areas without mechanical units, or for fragile or difficult to clean instruments. With manual cleaning, 2 essential components are friction and fluidics. And again, that's a very simple statement, but then you think, well, Absolutely. You know, when we describe friction as rubbing or scrubbing a soiled area with a brush, cloth, something like that, absolutely, that direct friction is an old and dependable method for lifting soils up. Once we have them lifted off, what do we really want to do after that? We would like to rinse them away. And that's where fluidics comes in. So that's fluid under pressure. And it's used to remove soil and debris from internal channels after brushing and when the design does not allow for passage. So if we're talking about, say, something from Intuitive, where there are long lumens inside those devices that you can't put a brush through. It is not recommended. So if you have those, I'm sure you're familiar with the IFU and just how much flushing or just how much fluidics is used to get those items clean. So 60% mechanical water impingement from spray arm technology. That's about where you're getting your most cleaning. It's a little lopsided to that. So we really, really need that impingement to work well. And we need our washer arms and our washer racks and the washer itself to be clean and really free-flowing to make sure that impingement action is doing its job, because it's about 60% of cleaning in a mechanical process. The other 40 does come from your chemical and thermal properties. So load size and configuration totally affect that, right? It affects both, really. It can stop impingement from happening well, and it can stop your chemical and thermal contact if loads are overloaded, if lids are not removed from trays, if multi-layer trays are put through the washer together. All of those are going to affect how that works. As I said, TIR 34 is the AAMI Technical Information Report on water quality. So it goes into defining those terms I've used a couple of times as we've gone through here. So section 4.2 reduces water to two categories, really. You have your utility water, which is water as it comes from the tap that might require further treatment to achieve the specifications. This water is mainly used for flushing, washing, and rinsing. Tap water is referenced frequently. So that's what you're going to hear most of the time. Someone's going to say tap water, what comes out when I turn on the faucet, you know, however that makes sense to you. That's really what utility water is. Oftentimes, we're finding out now we need to go past that, and that's where critical water comes in. Water that is extensively treated, usually by multi-step treatment process that can include a carbon bed, softening, DI, an RO, or distillation. So to ensure that microorganisms and the inorganic and organic material are removed from the water, a final submicron filter could also be part of the treatment process. A lot of times we want this critical water, especially in the rinse, because the more we take out of water, the more we pull away from it, the more it wants to pick up other things. So as we treat water and then we use it to rinse, it actually increases its capability of rinsing away and drawing things away from the instruments, which is what we want the most in our final rinse. Now we're going to talk about ST79, loading mechanical washers, 76432, remove all pre-soaked chemicals either manually or mechanically before loading into the washer. Open hinge instruments, use hold down screen, silicone, rubber mats should be removed. All of these are to make impingement work. And as we talked about, 60% of the cleaning. ST79 also talks about cleaning agents in 763 when using an automated chemical delivery system or device or sink proportioner. The automated doser should be routinely verified and calibrated. Again, this chemistry and water work together, and if we're not making sure that that automatic doser where we're just pushing the button is actually giving us what it says it should when it should, we can have problems. There are a few various sections that talk about water in SD79, water quality for various decontam processes, and water quality monitoring systems. It also talks about steam quality, incoming water hardness, pH, ion content, and alkalinity, and then processing water, have a source of critical water for your final rinse that comes from TIR 34, rinse with water of a quality specified by the device manufacturer. We talk about IFUs all the time. So many times we talk about them for sterilizing and things like that, and we talk about them for cleaning as the way that the manufacturer proved to the FDA that it could be cleaned. Do we consider the water? We absolutely should, because it's in there. It should be pre-treated with initial cold water rinse with running tap water. Follow the detergent manufacturer's written IFU for all of those items to make sure that the detergent is suitable. So water quality also includes having and using the proper temperature. Examples from instructions for use. I just have a few here. Use distilled, demineralized water if possible. So that comes out of an IFU. During the surgical procedure and immediately after, remove gross blood and debris, rinsing instrument in distilled water. That's probably something that's very susceptible to rusting and things like that, and they're trying to use the most treated water that they can. Consult manufacturer's guidelines for settings. Add 1 to 2 ounces per gallon of warm water. Soak instruments 2 to 3 minutes or longer if required. 20 or 15 to 20 for difficult stains. So that here is talking about warm water, so a specified amount of detergent versus with warm water, and then giving 2 different times depending on your soil and staining. Effective at room temperature, which is 68 Fahrenheit, but use of the product with warmer water, 90 to 110, will optimize performance. So there you go. That is a manufacturer specifically saying if you use this at a specific temperature, it will work better for you. Here is a little piece from an intuitive IFU, actually, and it talks about water under pressure. Confirm that the water is pressurized to 30 PSI or 2 bar. So if you are processing a DaVinci Xi instrument and you do not have your water pressure at 30 PSI, you're not actually following their instructions for use. So now, why do we monitor? Water hardness can be easily monitored with a colorimetric dipstick. This is a simple way to test and monitor water quality. If the dipstick indicates the level of water hardness is increasing, a more thorough test should be conducted. But that means there are truly simple and quick ways to do it. Often detergent manufacturers are willing and able to conduct water quality testing for free. So you may realize that you have a little bit of a problem. Try to leverage your detergent manufacturer, because they want to keep your business. They want you to believe their detergent works well, and they might come in and do a little water testing for you to try to see if there's any issues. You would fix those issues, and then you would love their product because it's going to work better. Other sources for testing, your washer company or your instrument manufacturer might also be able to help you out if you were to ask. 4 steps for monitoring. You want to assess your water quality. You want implementation of water treatment process, assurance of proper water quality for various stages in your device reprocessing, and then ongoing water quality. And you can sort of think about that. There's a way to start. Here's how I'm going to do it. And here's how I'm going to continue to make sure that it is working properly as I move on. We're going to just break down these water treatment methods a little bit. These are your ways of getting critical water. As we talked about before, we talked about RO, that's reverse osmosis. That removes dissolved organic solutes. It removes microorganisms, including bacterial endotoxins. And it requires regular maintenance, including membrane replacement and pre-filter replacement. Now we're going to talk about DI. That removes anions and and catons, regular replacement of pre-treatment filter and regeneration of resin filters does not remove bacteria or bacterial endotoxins. That's not what DI does. Use as a primary means of purification is not recommended. So that's not, that's not quite, because of the endotoxins, that maybe not the primary means. We did just from my own experience, we used to get notified from facilities, we are changing the resin beds. Please refrain from using the water until you hear from us. So that may be something that happens with you as well, that your facilities department or whoever is helping you maintain the whole water system may reach out to you and say, hey, please, don't run your washers right now. Let us do our job and then get the system back up and running. Ultrafiltration, that's where membrane-based device used to remove particles down to 1,000 Daltons, and that can remove bacteria and bacterial endotoxins. And then distillation. So when you have distilled water, that removes bacteria, inorganic and organic solutes, and endotoxins. Storage tanks are required. Our storage tanks require regular sanitization. If you want it to stay distilled, that's something that you have to work on with the storage tank. And resistivity of water requires regular monitoring. Now we're on to our last objective. Understand how poor water quality can contribute to poor outcomes in patient care. We think of the ruler and it's like, oh, that's just a ruler. That's going into a sterile tray. It could be placed in a body cavity. Would you want all of those water spots? And we're hoping that those are water spots, right? And I'm actually gonna show you something in a couple of slides where maybe those aren't just water spots, and that's when it's an even bigger issue. Still, I wouldn't want that in my body if someone could look at it and make sure that it was taken care of properly. Biofilms are a big, big thing. It's why we have to clean endoscopes so soon. We have an hour to get that started because of biofilm formation specifically. So biofilm forms when bacteria adhere to the surface in a wet environment and begin to excrete a slimy glue-like, it's really extracellular material or substance that can anchor them to all kinds of materials such as metal, plastics, soil particles, medical implant materials, and tissues. And it happens so quickly. They can start to form within minutes, and then they just proliferate as time goes on. So what kind of stuff do we find in biofilm? E. coli, Legionella, Pseudomonas, all of the things that we do not want to find. Cleaning is hard enough without allowing things to grow and to proliferate and then have to deal with them and take them out after. So these are just a few examples of the things that you can find. And when you start getting into the gram negatives, that's really when it becomes a big thing for endoscopes. And here's another example. You may not think of it exactly that way, but poor water quality equals biofilms. And some of the things that you see inside washers and things like that really are the start of a biofilm and can have worse effects on the whole process. So microbial biofilms on a surface cost the nation billions of dollars yearly in equipment damage, product contamination, energy loss, and medical infections. And that came from a Montana State University article about biofilms. So here is really what I wanted to mention when I was talking about that ruler. So poor water quality is dangerous when debris is mistaken for water spots or rust. Now I know the pictures on the right don't look really good at all. I wouldn't want either one of those, that sharp towel clip or that needle holder, used on me, but I would like you to actually think of it. The towel clip did not actually have any blood on it. It looks awful, but that didn't have any blood. So if I'm thinking to myself, well, my water quality is just not good, so my instruments just don't look great, and I'm sure that this needle holder just doesn't look great, just like the towel clip, and it's fine. The needle holder actually had blood on it, and there are tests to start to show that. And it's really even more, kind of goes back to the picture of the ruler with the small osteotomes on the left. Those just look like hard water stains, just look like water spots, and there's a small green speck on that swab that actually shows that that's blood. And I just want you to see in the middle. I wear glasses. None of you can see me now, but you saw my picture in the beginning. I wear glasses, and still I have trouble seeing 0.1 microgram, right? If you look at that little swath in the middle between the two bottom pictures, that's just what a dollop of bioburden of blood can look like at 100 micrograms. At 10, both of those are pretty noticeable as blood. I don't think I would have a problem doing that. At 1 microgram, boy, that's getting a little tough. And at 0.1 microgram, it really just looks like a little watermark. If you hit it just right in the light, you could actually see it, and you say, well, that's just a little watermark. Well, there are tests out there that can measure down to 0.1 microgram, and you could find out that is actually, it's actually blood and not just water stains. But again, as we talk about water quality, if we allow our water quality to sort of lull us into a thing where we say, well, the instruments just don't look good because my water's not good, we may miss something that isn't a water quality issue, it's a cleaning issue, and that becomes a much bigger and much more problematic thing. So packages ready to use, and here we are. We talked about it a little earlier on, that some of these things, some of these water quality issues end up coming out in our packages, and we see them as where the water has dried up and left behind the minerals, the chemicals, whatever was in the water that we didn't want there, end up coming out in our packages. If I was in the operating room and I was opening, if I was scrubbing and opening these peel packs or about to open that wrapped item, and I were to see that, I would question it. I would question it absolutely. And I don't think that just saying, well, we just don't have the greatest steam quality. I'm sorry, we don't have the greatest water quality. You may see that kind of stuff. I don't think that answer is going to be deemed acceptable. It's something they're supposed to inspect packages when they open them for things like holes and stains and things like that. So a scrub who's on top of it is going to look at these and most likely reject them. The worst part is if you only have one or two of an item or they all look like that, you may put yourself in quite the bind with not being able to deliver what they want because all of your packages really don't give anyone confidence that they're ready to use. Okay, so we've just got a couple of things. Poor water quality, if left untreated, will increase your cost to do your work. It's going to cost you more in chemistry. It's going to cost you more in time. It just costs. So, and there are ways to figure out if you have water quality problems, and there are ways to fix it. So it's not something that should just be left. And so if you see a spot, you should check it out. Again, we just mentioned at the end here, there's ways to do that spot identification and find out if it's just a water quality issue or if it's really debris. And we really should be taking care of the water quality issues so that whenever we see a spot, we don't just dismiss it as poor water. Know what type of water you need to use at each stage of reprocessing and monitor it on a regular time frame. It's supported in standards. It's something that if you're going to comply with IFUs, you have to be doing it. So if it's not something you're actively doing now or thinking about, it's something that you really should. You want to work with your facilities department most of the time, right? Once you get past the drain, or once you get past the first elbow where your equipment is fed with water, the equipment manufacturer says, that's not my part. That's you, that's your facilities infrastructure, so that's not really my part to help you out with. So you really want to work with the facilities department. They are monitoring water. On what level, it's hard to say, but they certainly are monitoring water within your facility. So they're a good person to have a conversation with to say, well, I'd like to talk about my water specifically in the CS, in the reprocessing department. You want to work with your vendor to get water quality testing done. Again, as I say, they won't fix it. They can't help you do that, but they will certainly run some tests for you. Many of them will and have no problem with doing that and do it for no charge because they want you to believe their machine and their detergent and their cleaning chemistry is giving you great outcomes. And if the water's hurting it, that's not helping them. It doesn't look good for them. And you can monitor it fairly easily. You know, like I said in the beginning, dipsticks, you know, there are some very simple tests out there that can be done. And then we can go digital. Now we have the technology to do some of that other stuff and plot it out too. So my closing thoughts, if IFUs and standards by themselves are not a silver bullet for poor practice, following the IFU is great. If you have poor water quality and you're not doing anything about it, it's not going to help you as much as you would like. IFU and standards help you get and maintain best practice, and they talk about water quality as monitoring it as a best practice. But you still need more common sense teamwork, certification, critical thinking, and other tools to help you do your job right. And that's why, you know, get your facilities involved. Have a conversation, read articles, participate in webinars like you're doing today, you know, elevate your thinking about all your processes, but today especially water quality. Here's just a little HealthMark again. We love education. That's a big thing. So there's a couple of ways to get some CEUs online. Crazy for Clean. If you order anything from us, you can use SPD dollars to do different things. We give speakers at no charge because we just want to get out and talk about what's right. And then we also support the Decontaminator of the Year. I was with the company at Isham this year and got to see us give out the Decontaminator of the Year award, which we've done for a couple of years in a row, and it's a great thing. And that is all I have. So looks like we've got just a couple of minutes for some questions.
Great. Thank you so much, Seth, for such an excellent presentation. We'll now begin today's question and answer session. Please submit any questions you have by typing them into the Q&A box you see on your screen. We will try to get through as many questions as we have time for. And the first question is from an audience member who would just like clarification on what pH stands for.
Yeah, right. We do that all the time. Little p, capital H, potential hydrogen. So that's why it's the capital H and the P doesn't need to be. So I know it's a little funky, but that's what it is. It relates to the hydrogen ions in a substance. That's why it's little p, big H.
Makes sense. Thank you, Seth. Another audience member is asking, can the drying phase of my wash cycle give thermal disinfection?
Yeah, no, I had mentioned that before, right? No, it doesn't matter that it gets above the 200. It doesn't work that way. The air does not conduct the thermal properties the way that we want it to, and it cannot be considered part of your thermal disinfection.
Great, thank you for clarifying that. Looks like we have time for about one more question, which is, why do I have to rinse off pre-soak sprays?
Yeah, I laugh because I'll do a little quick funny thing. For one, it's in the IFU, right? So most of them, if you're reading them, it's actually in the IFU. Second, chemicals, they're proportioned right in your washer, right? They're specifically set to come in. You're actually adding extra chemistry, and that's not good. And the reason I chuckled is because I have kids, and one time they put a little Dawn dish soap on something and didn't rinse it off, and we put it in our dishwasher, and then as it belched foam all over the floor, I was like, oh my goodness, what happens? And so really that's kind of a silly example, but that's how that works. Too much chemistry.
Never a thing. That's a great example. Thank you. Well, that is all the time that we have left for today. I want to thank Seth and Healthmark Industries for their insightful presentation and to our audience for participating. Please enjoy the rest of your day, and we look forward to having you join us for future webinars.